Hello. In the previous lecture, we discussed direct mapping in detail. Now let's move on to the next type of mapping in cache memory, which is n-way set associative mapping, or in general set associative mapping. Okay, so we had discussed the let's say terms capacity of a cache, that is how many words in total it can handle, then n, which is the number of blocks per set, then s, the number of sets in the cache, right? And we had said that in direct mapping n was 1, right? That is, for every set there is only one block, and therefore number of sets would be equal to number of blocks in the cache memory, and in the earlier case therefore s was 8. Now what we are doing is, here for this example we are taking the same cache which is of size 8 words, but we are making n equal to 2, that is a two-way set associative cache. So this is how it will look. So the total capacity is only 8 words, but there is 4 sets of 2 blocks each. So this is the first block, this is the second block. Alright, block 1, block 2. Again, for each set there are 2 blocks. So 4 sets of 2 blocks each, that is 8 blocks. This is the way this cache memory, that is a two-way set associative cache, is arranged. And here what is happening when suppose a memory has to be, a location, a data word has to be stored in the cache, then what happens, it will again same thing here, it will look for the set, okay, which set it is there. Then after finding the set, here since there are only 4 sets, the number of bits, set bit is 2. Earlier it was 3 because there were 8 sets. Now here are only 2 set bits. Now suppose the two set bits of a specific word is 1 0, right? Then it will come into this set. Then it will just copy it into the either one of these. Once within a set, there is no specific method or any algorithm or anything to determine which block it is the data is copied into within the cache. That is, once you bring the value here, it can be stored here or it can be stored here, it doesn't matter. So like suppose if this is filled and this is empty, then obviously the new one will be copied here, or otherwise if this is filled and this is empty, then the new one will be copied here. Otherwise, if both are empty, or if it is a set of 4 words and 3 of them are empty or 4 of them are empty, then there is no specific order or way or rule by which the blocks are copied within the set. Only that the specific set is determined using the set bits. Within the set there is no specific rule. That is, there is a sort of flexibility. Earlier in the direct mapping, the problem was that lack of flexibility, right? But in multi-way or n-way associative mapping, there is this flexibility. So here for this specific example, once the set is fixed, then that is, if you want to test whether this specific data is there, that is a specific data stored which is supposed to be stored in a specific location, the memory is there in the cache or not. How do we check? Again, we compare the tag bits, right? So first we compare the tag bit with the tag bits of this one, and we compare the tag bits with the tag bits from this block for a specific set. So 2 comparisons are there. Again, like in the previous case, we check the valid bits, right? So earlier this was the one condition for hit. Now we have to check for each block. Suppose if there are 4 blocks in a set, then like this 4 gate combinations will be there. and instead of this one multiplexer, this 2 by 1 multiplexer, there would have been a 4 by 1 multiplexer, right? This is how two-way set associative mapping of cache of 8 word size is implemented. So here the thing is that the hardware complexity is getting larger, right? 2 comparators are required. Even though we are just showing this comparator using one block, it is a larger unit depending on the size. Here the data is a 32-bit data, right? One word is, sorry, it is a 28-bit tag. So a 28-bit comparator is required here. So 2 28-bit comparators are required here. If it is a 4-block set, then 4 comparators would have been required here. Like that, depending on the condition or configuration we are using, the complexity will reduce or increase. But anyway, compared to direct mapping, the complexity, hardware complexity required for set associative mapping is higher. Okay, now let's see a problem. Repeat example 8.7 using 8-word two-way set associative cache from figure 8.9, right? This was problem 8.7. Here we had two memory location which had the same set bit, right? Two same set bits, and therefore they were copied into the same set, and as a result of this being a direct mapping, there was a constant conflict and the miss rate was 100. Now let's see how the same problem will be solved using the two-way set associative mapping. Here also the set bits are not changing, right? For this condition, the set bits are the same. So again, it will be copied into set 1 only. And here the thing is that set 1 has 2 blocks. It is a two-way set associative mapping. That means 0x4 can be copied in one block and 0x24 will be copied in another block, right? So what happens during the first iteration, when it looks for 0x4, it will be a miss and it will be taken from main memory and copied here. So that is one miss. Again, this in the next instruction, 0x24 will be a miss and it will be taken from memory and stored here. But after that, since both of them are here, for the next 4 iterations, what is happening? It is a hit. So here, what is the miss rate? 2 out of 10, that is 20%. So just by increasing, by implementing a different type of association mapping, the miss rate went down from 100% to 20%. That is a drastic change. That is a advantage of this multi-way set associative mapping compared to direct mapping. The problem with direct mapping being a constant conflict is there. Okay, moving on to the next one, which is a fully associative mapping or a B-way set associative mapping, same thing. So here what is happening? Here there is only one set, right? Only one set, and all the blocks are in that set. So it is completely flexible. There is no issue of where the data will go and anything like that. So if there is an empty spot, the new block can be accommodated there. But the problem is that if we draw the comparator and the hardware implementation of retrieving data from this one, it is very complex, right? So 8 blocks are there and 8 comparators are required, and an 8:1 multiplexer will be required. So it gets very complex. That is a big issue with this one. So other than that, there is no significance to this fully associative mapping. Okay, now let's consider the same cache, that is an 8-word cache. Again, we are considering direct mapping. with a slightly different configuration. Here from the figure, can you identify what is the change? Here what we had done is, instead of taking one word per block, we are taking 4 words per block, right? 1, 2, 3 and 4 words per block we are taking. Along with the data, obviously there is the tag region and the valid bit. So we are taking 4 blocks of data, 4 words of data for each block, and hence it is a 8 word cache memory, and it is a direct mapping. There are only 2 sets, right? Now here we introduce a new term, which is block offset. But before that, what is the purpose of going into or increasing the number of blocks per set? Words per block. My mistake. What is the point of increasing the words per block? Because when we are using only one word per block, or if the number of words per block is less, we are only able to use the concept of temporal locality to its fullest, because we are just trying to take the data which is being frequently used. But the purpose of cache is to exploit one more concept, which is spatial locality. That is, when we are taking a word or of data from the memory, the chances of the consequent or nearby data words being useful is also there. Therefore, we are going to increase the number of words per block. So what is the impact or consequence? That is, if you want to read, suppose a particular word number maybe 1, 2, then when we are using like this 4 words per block, we are not just taking 1, 2 address 1, 2. We are taking address 1, 2, 1, 3, 1, 4 and 1, 5. We are taking 4 words together and putting it into the block. That is the advantage, right? So this is how you implement it. So now coming back, the new new term or new bit of information is block offset. So what is the block offset used for? Block offset, it will indicate the location of the data word within the block, right? So 0, 0, 0, 1, 1, 0 and 1, 1. So that particular word you are looking for can be in either of these locations within one single block. And because 4 words per block, we need 2 bits of block offset. And because we only have 2 sets, we only need 1 bit for set, right? And this block offset can be used in a multiplexer like this to select which word is being read out as data. And again, this being a direct mapping, only one comparator is required. Okay, now let's see a problem to see how this increasing number of words per block improves our miss rate. Okay, repeat example 8.6 for the 8-word direct map cache with a 4-word block size. Let's see the question. So this was our question to use this particular program and how we are using the cache for this. And again, what was happening, we had 3 reads, right? We had 3 memory access, and we were copying from locations 4, C and 8. So in our continuous memory location, it will be 4. This will be one word, this will be the next word, and this will be the word after that. So let's see how this problem translates into the multi-word block scenario. And here the miss rate was 20%. So let's see. Okay, so this will how it will be for a 4-word block. When we in the first iteration, the first value to be location to be read was 0x4, right? And as a result, the data from 0x0 to 0xc is being copied. That is, 4 words are copied, and the reason it is read from 0x0 to 0xc is because the blocks are arranged in the main memory in that way. So memories 0x0, 0x4, 0x8 and 0xc will be copied into the cache. So it is in the first load word condition for 0x4, it is a miss that is there. But after that, for every load word, that is for load word using 0xc and 0x8, it is a hit. Again, in the next iteration, obviously these are here, so there is no issue. So what is happening? There is only one miss, that is in the initial case, and after that there is one miss, and after that everything is a hit. Therefore, miss rate is 1 by 15, which is 6.67. That is, originally when you are using a direct mapping, simple direct mapping, it was 20%. Now again we are using direct mapping, but we have increased the words per block. Then the miss rate has come down to 6.6%. So with this, with this example and the previous example when we did n-way associative mapping, we can see how adding number of blocks per set and number of words per block affect the miss rate, right? But this cannot go on indefinitely, as hardware complexities will be there, and there should be some balance. Okay, now let's wind this mapping techniques, wind up these concepts. So when we are talking about cache, we have to talk about 3 things: the total capacity, then block size, that is number of words per block, and number of sets in a number of blocks in a set, that is n. And this is a comparative table of the number of ways, that is associativeness, and a number of sets. So for direct mapping, there is only one block per set, and there are b blocks. Number of sets is equal to number of blocks. There are b sets. In fully associative mapping, there is only one set, and that is a whole cache is one set, and number of blocks in a set is b, that is total number of blocks. And set associative mapping is something in between, right? So as we increase the number of blocks per set, then we can reduce the miss ratio. Also, as we increase the number of words per block, then also we can reduce the miss rate. But the thing is that as we keep on increasing the number of words per block, then total number of sets will also reduce. So that is an issue. Again, conflict will occur. So when it comes to designing, some let's say balance has to be found. So with this, I am winding up the session on mapping of cache memory. In the next lecture, we will talk about replacement strategies and writing policies, and with that we will wind up cache memory. Thank you.